Z parameter of two-port circuit. In two-port circuit, we have four terminals. 1 dash, 2 dash. To make one port, we need to have two terminals. So this one is port 1 or input port, and this is second port or output port. Since we have two ports, we can apply excitation and take the response from these two ports. And in this two-port circuit, voltage here, port 1 is V1, current at port 1 is I1, voltage at port 2 is V2, current at port 2 is I2. I1 current is going into the two-port network, and I1 current is coming out from the two-port network through this input port. Similarly, I2 current is also coming out through this port 2. In this two-port network, no energy can be stored. No energy can be stored in this two-port network. And the two-port network circuit or two-port circuit should not have any independent source. Dependent sources are allowed, but independent sources are not allowed within the two-port circuit. And we should not apply any excitation between 1 and 2. No excitation should provide between terminal 1 and 2. Similarly, 1 and 2 dash, and 1 dash and 2 dash, and finally 1 dash and 2. Now the Z parameter for this two-port network or equation for Z parameters are V1 Z11 I1 plus Z12 I2. This is first equation, and second equation is V2 Z21 I1 plus Z22 I2. Here I1 and I2 are independent. We can also write these two equations in the matrix form. This matrix is called impedance matrix or Z matrix. Now, the Z11 is V1 upon I1 when I2 is 0. So it is simply the input impedance. Because it is the ratio of voltage at port 1 to the current at port 1 when port 2 is open circuited. So it is input impedance when port 2 is open because I2 is 0, and Z12 is V1 upon I2 when I1 is 0. It is called a reverse transfer impedance. When port 1 is open circuited, because it is the ratio of voltage at port 1 to the current at port 2, or voltage of input port to the current of output port. That's why it is reverse transfer impedance. Now this Z22 is, sorry, Z21 is V2 upon I1 when I2 is 0. It is called forward transfer impedance. Because it is the ratio of voltage at port 2 to the current at port 1 when port 2 is open circuited, or it is the ratio of output voltage to the input current when output port is open circuited. And then Z22 is V2 upon I2 when I1 is 0. It is output impedance. When port 1 is open circuited, because it is the ratio of output voltage to output current when input port is open circuited. Now we have reciprocal two port network or reciprocal two port circuit. When V1 by I2 when I1 is 0 is equal to V2 upon I1 when I2 is 0, then the circuit is called reciprocal circuit, or Z12 is equal to Z21, then the two port circuit is reciprocal. Then we have symmetrical two port circuit. When V1 by I1 when I2 is 0 is equal to V2 by I2 when I1 is 0, or when Z11 is equal to Z22, then circuit is called symmetrical two port circuit. Now we can draw the equivalent circuit for Z parameters. Equations are V1 equal to Z11 I1, Z12 I2. Second equation is V2, Z21 I1 plus Z22 I2. In the first equation, in left side we have voltage of port 1 or input port. So this is the voltage V1. In the right hand side of equation we have two terms, and two terms has to be voltages, and here we have the addition of two voltages, means these two components are connected in series. I1 is the voltage at input port or port 1, and Z11 is the impedance. So the impedance is here. Now I2 is the current at port 2, and I2 is independent of I1. It means this component is the dependent source, current dependent voltage source, and its value is Z12 I2. This voltage source is depending upon current I2 of port 2. Now in the second equation, in the left hand side we have voltage. So in the right hand side the two quantities has to be voltages, and the sum of voltages is possible when the two components are connected in series. So voltage at port 2 is V2, current here is I2. So the drop Z22 I2 is here. So impedance Z22 is connected here. Now the second term is Z21 I1, and I1 is the current at port 1. It means this quantity has to be a voltage source, current dependent voltage source, which is connected in series with Z22, and its value is Z21 I. In fact, Z21 I1. Now let's find out the Z parameter for different circuits. T network or T circuit. Three impedances are connected in the shape of T. This is port 1 with voltage V1, current I1, voltage V2, current I2, and the impedances are ZA, ZB, and ZC. Now we have to find out the Z parameter for this T network. We can see that I1 current is coming from port 1, I2 current is coming from port 2. So current through ZC is I1 plus I2. Now we can apply KVL in loop 1 and loop 2. KVL in loop 1, rise in voltage V1, then drop ZA I1, and then drop ZC I1 plus I2. We can rewrite this equation as V1 equal to ZA plus ZC I1 plus ZC I2. This is first equation. Now KVL in loop 2. So rise in voltage V2, then drop across ZB, which is ZB I2, and then drop across ZC, which is ZC I1 plus I2. So this equation is V2 ZC I1 plus ZB plus ZC I2. This is the second equation. We can write these two equations in matrix form. So this is ZA plus ZC, and then ZC, ZB plus ZC, I1, I2. So this is basically Z matrix. Or we can say Z11 is ZA plus ZC, Z11 is ZA plus ZC, Z12 is ZC, Z21 is ZC, and Z22 is ZB plus ZC. Now in this circuit we can see that Z12 is Z21, hence this circuit is a reciprocal circuit or reciprocal two-port network. Now let's find out the Z parameter for pi network. In this pi network, the three impedances are connected in the shape of pi. And the impedances are ZA, ZB, and ZC. Now this is basically a delta network. The three impedances are connected in the shape of delta. So let's make delta to star conversion. We will convert this delta network to star like this. Say this one is Z1, this is Z2, and this one is Z3. So Z1 is basically ZA ZC over ZA plus ZB plus ZC. Similarly, Z2 is ZB into ZC over ZA plus ZB plus ZC, and Z3 is ZA ZB over ZA plus ZB plus ZC. So that's how we convert a delta network to star. So now we can redraw this circuit. The pi network is converted into T network through delta to star conversion. This one is Z1, Z2 and Z3. And for the T network, we know that Z11 is Z1 plus Z3 and Z12 is Z3 and Z21 is again Z3 and Z22 is Z2 plus Z3. So for the pi network, by converting the pi network to T network, we can simply find out the Z parameters. Now let's take another circuit. Suppose we have a two-port network, something like this. The current here is I1, current here is I2, and this impedance is suppose Z or Z. And we have to find out the Z parameter for this two-port network. Now, in this circuit, we can see that current through this impedance is I1, which is coming from port 1, and I2 current is coming from port 2. So we can simply write I2 is minus I1. So we can see that I2 current is depending upon I1 or I1 current is depending upon I2. It means I1 and I2 are not independent. And for Z parameter, for any network to exist, I1 and I2 has to be independent. But here I1 and I2 are dependent. So Z parameter for this network or for this circuit does not exist. Why? Because I1 and I2 are dependent. Let's take another circuit. In this two-port network, the impedance Z is connected like this. This is port 1 and this one is port 2. Now we have to find out the Z parameter. So current through the impedance Z is sum of the two currents I1 and I2. Now by applying the KVL in these two loops, we can find out the Z parameter. So KVL in first loop is V1 drop across Z which is Z I1 plus I2, or we can simply write V1 is Z I1 plus Z I2. This is the first equation. KVL in second loop, rise in voltage V2 and then drop across Z which is Z I1 plus I2. So V2 is Z I1 plus Z I2. So from the two equations we can write that Z11 is Z, Z12 is also Z, Z21 is Z and Z22 is also Z. Since Z12 is Z21, the circuit is reciprocal, and Z11 is Z22, it means the circuit is symmetrical also. Now let us find out the two-port Z parameter for lattice network. This is lattice network ZA, ZA and the impedance ZB is connected here. ZB is connected between 1 and 2 dash. 1 dash, 2 dash, and one more ZB is connected between 2 and 1 dash. This is ZB. Now we have to find out the two-port network, Z parameter for this lattice network or lattice circuit. In fact, this is I1. I1 is coming out here also, I2 is coming out here also. Now, to find out the Z parameter of this lattice network, we will bring 2 dash, or we will bring 2 dash in the position of 1 dash and 1 dash in the position of 2 dash, or simply unfold, we will simply unfold this circuit. One, 2 dash, this is 2, 1 dash. This is ZA, this one is ZA. Now between 1 and 2 dash, ZB is connected. So 1 and 2 dash, ZB is connected. And between 2 and 1 dash, ZB is connected. This is ZB. This current is I1, and at I1 dash current is also I1. Here current is I2, and current at 2 dash is I2. Now the voltage between 1 and 1 dash is V1. This voltage is V1. And the voltage between 2 and 2 dash is V2. Now we'll apply KVL, KCL to find out the Z parameter. So let us suppose that I2 is 0. We'll make I2 0 so that we can find out Z11, which is V1 by I1 when I2 is 0. And similarly Z21, which is V2 by I1 when I2 is 0. So if we make I2 0, it means no current is coming in from the 2-port terminal 2. This current is 0. And no current is going out from 2 dash, or no current is going towards 2 dash. So the circuit looks like this. It means for this I1 path, for this I1 current, we have two paths. One path is through this ZA and ZB, another path is through this ZB and ZA. It means from 1 to 1 dash, we have two paths with the same impedance ZA plus ZB. So the I1 current will simply divide by 2. The current through this path is I1 by 2, and current here also is I1 by 2. Now we can apply KVL to find Z11 and Z21. So from 1 dash to 1, rise in voltage V1, and then the drop is ZA plus ZB, and the current is I1 by 2. So we can write V1 as ZA plus ZB by 2 into I1. So V1 by I1 is simply Z11, V1 by I1 when I2 is 0 is Z11, and it is equal to ZA plus ZB by 2. So this is Z11, and for Z21 we will apply KVL in this path, rise in voltage V2 and drop across these uh, ZB and ZA. So rise in voltage V2, and the voltage drop across ZB is ZB I1 by I2, and here there is a rise in voltage because current is coming in this direction. So rise in voltage across ZA is ZA I1 by 2. So this equation is V2 equal to ZB minus ZA by 2 into I1, or V2 by I1 when I2 is 0 is simply ZB minus ZA by 2, which is equal to, better to write here, which is equal to Z21. Now we have two parameters, Z11 and Z22, and to find the other two Z parameters, Z22, which is V2 by I2, will make I1 0. Similarly, to find, we can also find Z12, which is V1 by I2, by making I1 0. So let's make I1 0. So let's remove this current I1, this current also at 1 dash. So for this I2 current, we have two paths, two parallel paths with same impedance ZA plus ZB. So I2 current will divide by 2 in the two paths because their impedances are equal. So let's apply KVL in this path. V2 rise in voltage, then drop across ZB, which is ZB I2 by 2, and then drop across ZA, which is ZA I2 by 2. So V2 is ZA plus ZB by 2 into I1. So we have now simply Z21, which is V2 by I1 when I2, sorry, this is I2. This current is in fact I2, yes. So this is Z22 when I1 is 0, and it is equal to ZA plus ZB by 2. Now to find Z12, apply KVL in this loop. Rise in voltage V1 and then drop across ZB I2 by 2, and here rise in voltage because current is coming from the opposite side. So rise in voltage is ZA I2 by 2 equal to 0, or V1 is ZB minus ZA by 2 I2, or Z12 is V1 by I2 when I1 is 0, and it is equal to ZB minus ZA by 2. So that's how we find out the Z parameter for the lattice network. Let us write all four Z parameters for this lattice network. Z22 is ZA ZB by 2, Z12 is ZB minus ZA by 2, and Z21 is also ZB minus ZA by 2, and Z11 is ZA plus ZB by 2. For the lattice network, again Z12 is equal to Z21, so this lattice network is reciprocal circuit, and Z11 is equal to Z22, so it is symmetrical also. Now let's do the analysis of terminated two-port circuit. Means for this two-port circuit, at port 2 the load impedance is connected, or this two-port network is terminated with this load impedance, and the excitation is connected at port 1. External voltage Vg with series impedance Zg. This is 1, 1 dash, 2 and 2 dash. Voltage at port 1 is V1, current at port 1 is I1. Voltage at port 2 is V2, current at port 2 is I2. Now this for this terminated two-port network or two-port circuit, we have to find out the input impedance looking from the port 1 or input port, which is Zi, or simply this Zi is V1 by I1, because when we look from the port 1 to the right of this port 1, there is no independent voltage source, so we can simply write Zi is V1 by I1. And now we also have to find the output impedance looking from the port 2 by removing this load impedance. For this output impedance, we have to make Vg 0, so that impedance has to be V2 by I1, assuming that the external source is connected at V2, because we will remove the load impedance. So V2 by I2 when the independent source here is 0. We have to find out these two impedances, Zi and Z0. So let's find out the input impedance first. The equation for two-port network is V1 Z11 I1 Z12 I2. This is first equation. V2 is Z21 I1 plus Z22 I2. This is second equation. Now we have to find out V1 by I1. V1 by I1. So this here we can see that V2 is minus ZL I2. This is equation 3. Substituting this V2 in equation 2, so we have minus ZL I2 equal to Z21 I1 plus Z22 I2. From this equation we can write I2 in terms of I1, so that I2 is Z21 I1 over Z22 plus ZL with negative sign. So this is I2 in terms of I1. Now substituting this I2 in equation 1, so the equation 1 becomes V1 Z11 I1 minus Z12 Z21 over Z22 plus ZL I1. So V1 by I1, which is input impedance, is simply Z11 minus Z12 into Z21 over Z22 plus ZL. So this is the expression for input impedance. Now we have to find out the output impedance. So let's make VG 0 first. Removing this external source. So this is short circuited. No need for this. Removing the load impedance. So two-port network has dependent sources. So we need to apply the external source with voltage say V2 and the external current is I2. So this Z0 is simply V2 I2. So first equation is V1 Z1 Z11 I1 Z12 I2. Second equation is V2, that is Z21 I1 plus Z22 I2. This is 1 and 2. Now from the input side we can write V1 is minus Zg I1. This is third equation. We'll simply substitute this V1 in equation 1. So this Zg I1 Z11 I1 plus Z12 I2. So now we can write I1 in terms of I2. So that will be Z12 I2 over minus Zg plus Z11. So this is I1 in terms of I2. Now substitute I1 in equation 2. So V2 is Z minus Z12 Z21 over Zg plus Z11 I2 plus Z22 I2. So V2 by I2, which is output impedance, is Z22 minus Z12 into Z21 over Zg plus Z11. So this is the output impedance. Coming back to the original circuit. Now for this circuit, can we find out the expression for current gain AI, which is simply the load current IL over the input current. This current is II, input current. So this IL is nothing but minus I2 and the input current is I1. So what should be the expression for the current gain? So here we can see that we have a relation in which we have written the expression for I2 in terms of I1. So this will give the ratio of minus I2 over I1. So current gain is minus I2 over I1. That will be Z21 over Z22 plus ZL. So this is the expression for current gain. Now, can we find out the expression for voltage gain also? Voltage gain, see suppose this V2 is V0, output voltage, and the input voltage is Vi. So what should be the expression for V0 over Vi, which is basically V2 over V1. Here this V2 or V0 is ZLIL, and this Vi, we can see that this Vi is Zi into II, because I1 is II, Zi, II. So voltage gain is ZL over Zi, and this IL over IL over II is AI. So the voltage gain is simply current gain into load impedance divided by the impedance. So that's how we do the analysis of terminated two-port network. Now let's see one example. For this circuit, we have to find out Z parameter or open circuited impedance parameter. Now, in this circuit, we can see that there is a pi network, and we need to convert this pi to T network, or this delta to star. The impedances are Z1, Z2, and Z3, or simply resistances. So Z1 is simply 2 into 1 over sum of all three resistances, 1 plus 2 plus 1. So it is basically 2 over 4 or 1 by 2. Z1 is 1 by 2. Similarly, Z2 is also 2 and 1, 2 into 1 over sum of all impedances. So Z2 is also 1 by 2, and Z3 is 1 into 1 over sum of all the resistances, 1 plus 1 plus 2. So this is 1 over 4. Okay, so now let's redraw this circuit. 2 ohm resistance, then Z1, and Z3. Z3 is 1 by 4 ohm. This Z1 is 1 by 2, so this make it to 1 by 2. And here Z2 in series with 3 ohm. And Z2 is also 1 by 2. So this is basically ZA, which is Z1 plus 2 ohm, means 2.5 ohm. This impedance is ZB, which is 3 plus 0.5, so 3.5 ohm. And Z3 is basically ZC, which is 0.25 ohm. So now this is standard T network, and Z11 is ZA plus ZC. So 2.5 plus 0.25 is 2.75 ohm. Z12 is ZC, so 0.25 ohm. Z21 is also ZC, so 0.25 ohm. And Z22 is ZB plus ZC. ZB is 3.5 and ZC is 0.25, so 3.75 ohm. We can also write this Z parameters in matrix form: 2.75 ohm, 0.25 ohm, 0.25 ohm, and finally 3.75 ohm. So that's how we find the Z parameter of given two-port network.